Hello, everyone, and welcome to session 17 on plane stress. Um, in this session, which will be broken into 3 parts, we're going to have the opportunity to cover some new concepts concerning how we can look at the state of stress at a given location. So we're going to do things where essentially we start with a 2D state of stress, like you see over here, and then rotate the element by some amount and look at these other stresses that can be associated with the same state of stress. So we're doing a transformation. And in this transformation, we will actually look at these elements, slice them like we slice our other members to perform equilibrium, and then figure out what these new transformed stresses should be. Okay, it'll become more clear as we go through this. In the second portion of our session, in part 2, we'll have the development of some generalized equations for 2D transformed elements. And then finally, in the third portion, we'll talk about stress tensors and rotations. We won't do all the derivations for Cauchy stress, but we'll show this useful relationship that allows us to do some of the same things we can do with generalized equations for 2D transforms and expand it to even 3D situations. And you might be asking, why is this information important? Well, when we cover criteria for failure, what we will learn is that some materials fail more due to shear. Okay, those are the ductile ones. And the more brittle materials actually fail more due to normal stresses. So what you're beginning to see here is that there are these transformations that happen as we rotate our perspective on an element that will magnify the shear stress or magnify normal stresses. And by understanding these relationships between normal stresses and shear stresses as we perform transformations, we can get to a state, or better said, an orientation where we have kind of maximum values for shear stresses or maximum values for normal stresses, and then be able to link these calculations to whether or not a material might fail. Okay, so let's go back before we get into all this math. Let's go back and just look at how we define or how we depict stress at a given location. The general state of stress has 6 components, and this is a slide, I think, back from session 4 where we talked about stress and strain. And we said that a tensor is a number or a collection of numbers that maintains its meaning under transformations, and that we could put these 6 components of stress into a tensor. Now, we'll get into this kind of near the end into part 3, but right now we're just trying to kind of look at how we can describe a state of stress in 3D. And in a moment, the next slide, we'll look at how we go from the 3D depiction to a 2D depiction that is useful for many cases that we might encounter. Okay, so this is kind of your typical 3D depiction, and yes, you can say, oh, we're missing some forces or some stresses on these other faces because I haven't made it transparent. Okay, that's yes, that is true, but you have the idealization that you have 2 stresses that are tangent to a surface that we typically define. One we define as being normal to a surface. So you can go back and look at session 4 if you want to get a review of these kinds of concepts. And we're reviewing them now as well. Okay, and this is the Cauchy stress tensor that we said that we could map to our sigma x, our tau xy, our tau xz, our tau yx, our sigma y, our tau yz, our tau zx, our tau zy, and our sigma z. Okay, sigma 1, 1, right? Sigma 1, 2, sigma 1, 3, and so forth, okay? So this is kind of the general 3D state of stress, or how we depict it. What is plane stress? Well, as you can imagine, plane stress is the stress in a plane. And we define it essentially to have a normal stress coming out of the plane, okay, coming out of the plane. So that's kind of a planar surface being 0, okay? And also that the shear stresses perpendicular to the plate, okay, so that those that might be coming out would also be 0, right? So essentially, as you see on this nice little figure, there's nothing on this face, there's nothing on the back face, right? Things are happening on this x face, right? In the x direction and in the y direction, okay, that'd be sigma x and sigma xy, right? And they're happening on this top face, this side face, and this bottom face, but nothing on this face right here and the one that's on the other side from it. And these are typically thin, okay, typically thin sheets. And we have actually been using some of the principles associated with plane stress already. The thin-walled pressure vessels are kind of a prime example, where we only have stresses, normal stresses, there's no shear stresses in the wall of the pressure vessel, okay? And even when we've been looking at combined loadings, or not even combined loadings, what we've typically been able to do is look at a state of stress at a given location on a bar, on a shaft, on a beam, and be able to say, okay, I can pick an orientation where I'm looking at stresses in 2 directions to keep my life a little bit simpler, okay? And it's still very powerful. It's still very powerful. As we've been able to tell, we can describe these combined loadings and the states of stress associated with them, okay? So as a review, we discussed the hoop stress, so sigma 1, and sigma 2, which we often call the longitudinal stress. And we also said that a sigma 3 component coming normal or in the radial direction of this cylinder, this pressure vessel, it's going to be negligible or small. And if you look at the video from the efficient engineer on understanding plane stress, what it says in that video, right, is that the stress normal or tangent, all right, so shear or normal stresses at an air interface are essentially 0, okay? And we can argue, well, maybe it's not quite that way on the inside, right? On the outside, sure, we can say it's pretty much 0 outside of this pressure vessel. On the inside, you say maybe it's P, all right? And as we discussed previously, even if we were to say there's some kind of really sharp gradient from, this P on this side, that pressure, okay, which is, has the same units of stress, and going to 0, because of the way these equations are set up, and we say that R over T has to be greater than 10, we're going to be saying that this sigma 3 is going to be much, much less, 5 times less in this case and 10 times less in this case. So again, we neglect the stress in the 3 direction here, in the radial direction. Okay? So that's what plane stress is. And so if we want to go from, say, a 3D element to a planar element, where we're thinking more about plane stress, we can draw similar to what we had, right, in that previous slide, where they had a nice little cube, and 2 of the faces were not having stresses on them. In that case, it was kind of the front and the back. In this case, we can say the top and the bottom are going to be the 2 faces where we don't draw any stresses. And then when we essentially kind of flatten, or we can argue rotate this element to get a 2D representation, right? So I'm just like, now I'm looking down at it. What am I going to see? I'm going to see essentially the stress elements we've been drawing all along. So, now we're calling it a planar element, all right? And we can write, our sigma x, our sigma y, as we see here, and then we can put on some shear stresses as well. And note with our convention, right, we've said that the positive tau xy is on the x face, right? So this is the x direction, right? So it's coming out. And then in the y, it's positive in the y, so it's up, okay, like we see there. And we've gone through this a few times now. Okay, so that's kind of how we define our plane stress. So how do we go about transforming? Or why do we transform? Okay. Well, yeah, we are defining this state of stress at a point. Okay. And it means that stresses on opposite sides of the cubes or squares are equal and opposite in magnitude, at least if they're normal, right? And if they're shear stresses, well, they can actually be causing a torque. So we need to balance them out by the the other faces that are 90 degrees relative to the pair. And we are kind of content. This is a state, all right? This is a state of stress. What happens when we rotate this planar element? Okay, so we go from what we've just had, what we've just drawn here, to something that is oriented like so. Okay, and kind of we show this in slide 2 of this portion. We are going to find an angle, okay, that we have here about which we do the orientation. And something that is subtle, or maybe not so subtle, but if you look at rotation transformations, what we are doing here is not rotating a vector into the same reference frame, xy, okay? What we are doing is rotating the reference frame itself, okay? So there's a subtle difference. I won't go into it right now, but maybe we'll talk about it a little bit in part 3, okay? But this is a rotation where what was sigma x is now been rotated to be sigma x prime. So this is essentially the x prime direction, and that angle that we've had in the middle of rotation can be thought of here. This would be the sigma x direction. This is the sigma x prime direction, okay? And we're interested in the stress in this x prime direction. We're interested in the shear stress in the tau x prime, y prime direction. We're interested in the normal stress in the sigma y prime direction. And there's an opportunity essentially to choose one of two angles. Either theta, when we start building triangles up, it's either theta or theta minus 90, or 90 minus theta, I'm sorry. Okay, because that's going to be, either the angle that you use for an opposite or adjacent, okay, and it'll become a little more clear in a second, okay. But what we need for these transformations is to maintain equilibrium. So stepping out, right, I said a second ago or a few minutes ago, the reason we care about this is because we want to be able to identify kind of increases in normal stresses or increases in shear stresses as we orient our element, okay? And in session 4, we said, tensor allows us to be able to do these rotations and maintain its properties, okay? If you look at that YouTube video, about what the heck is a tensor, right? That's one of the main themes that keeps getting emphasized. Okay, so just to try to kind of give a little bit of perspective, this is a figure that we showed previously, okay? And we said, look, I can have a resultant force if I have these two balls, two spheres, or whatever. I have some structure, and I slice right here, okay? And then looking at the internal force, right? Just like we have shear force and bending moments, and when we do beams, right, or we look at normal axial loads and beams or bars or shafts even, right? And so, but I remember I'm taking a slice at a particular orientation. So that is going to give me some type of resultant force and a set of stresses, okay, on that surface, right? That's at some particular orientation, as we see here. So like, it's going to be like this delta F over this delta A, right? Some kind of small stress. But what happens if I go through the same exact location, but I do a slice at a different angle? All right, let's say now, I'm going kind of like this. Well, these forces and internal stresses are still there, okay? But they are, if I define them now relative to this different slice, right, I'm going to have a different vector, right, with a different magnitude that's describing the state of stress at this location. So what we're doing is now creating a tool where we can do some rotation of a planar element and be able to look at how stress is essentially, or how the perspective or how the depiction of stress looks if you cut or do slices at different angles. Okay, that's pretty much what we're getting at here. And then we can say, oh, shear stress is increasing, normal stress is increasing, and if my material is going to fail by shear, and I know what the shear strength is for that material, okay, this is how close or how far I am from the maximum shear stress, for example, in the structure. Okay, so how do we do these transformations? That's pretty much the meat of, I've kind of tried to motivate what we're doing, but how do we do these? Well, we start with an element having a known stress, and then we rotate it by theta, okay? And we're going to take a cut with the exposed face perpendicular to this x prime. Okay, so this is now our new, oops, that got a little bit cut off here. But this is this is x prime. Okay, sorry, my images, that's x prime, this is x prime, y prime. In this tau x prime y prime is the vector associated with the shear stress now, okay? And so we're going to take a cut to expose this face perpendicular to x prime, which is in this direction. So what does that look like after we finish putting all these other stresses on it? Okay. It looks something like this. Okay, this is that face now, all right? This is perpendicular to x prime, all right? This was x, this was the y, okay? But this face is now perpendicular to the x prime here, okay? And it has this angle, all right? So now we've gotten to this step. This direction, okay, is going to be in the y prime direction, okay? And we are actually going to do something a little bit interesting with respect to being able to do equilibrium. We are going to be very careful because these stresses are not, like the sigma x is not acting in the same direction as x sigma x prime, right? And it goes for sigma y and sigma y prime, tau xy and tau xy, tau x prime y prime. What we need to do is go back and create forces on this element to keep it in equilibrium, kind of like we did just, with the plane stress elements, right? We said, okay, look, there needs to be a balance of forces so that this is not accelerating and it's not rotating. So it's a small element, and we say this face is going to be what we call a small delta A, okay? But notice, this face is the hypotenuse of this triangle, so that this face and this face are going to be smaller, and they're going to be related by trigonometric relationships. So this theta is really in this corner here, okay? And one thing I suggest is that when you draw these, I'll say this a couple of times, and there's even notes here. when you draw these triangles, make them exaggerated, right? So even if theta is equal to 45 degrees, right? Go ahead and say maybe it's like really like a 15 degree, right? So that you can see theta would be in this corner, and this is going to be the opposite, which is delta A sine theta. And this one over here is going to be the adjacent, which is delta A cosine theta. Okay? So it's just a little trick to keep track of these things when we do equilibrium. Now, here's the triangle, same triangle, okay? Same angle in there. And we now say that since sigma x prime is acting on this face with this area delta A, we can say that the force coming out of that face associated with sigma x prime is sigma x prime delta A. And you get the same idea for tau x prime y prime delta A. And over here, this original sigma y, all right? So sigma y is coming out of the top and the bottom. Out the bottom, right, it's acting on this delta A sine theta, okay? And tau xy, right, which was over here, is also acting on the bottom. And it's also acting on the side, this left side, as is sigma x, the original sigma x delta A cosine theta. So now, what do we have? We have a structure, it's a triangular structure with some area, and we can balance the forces on this structure. There's one more point that we had to keep in mind, and we'll show that in the example, and that is still this sigma y delta A sine theta is not acting in the same direction as either tau x prime y prime or sigma x prime, right? Same thing goes for this orange shear stress, this orange shear stress, this orange normal stress. These are still not acting in the same direction, okay? So what we actually need to do, and we will do, is think of these vectors as being hypotenuses? I don't know what the right word is, but this is gonna be a hypotenuse that allows us to then map the appropriate component or components to these new directions, okay? Now, another thing you might see here or might have noticed is that we have sigma x prime, tau x prime, y prime, but there's no sigma y prime. So for sigma y prime, we actually had to take another slice oriented in a different direction. Okay, so you see this face is now parallel to this face right here. And we can have, again, the same angle, all right? And now we can put our sigma y prime delta A coming out of that top face. This tau x prime y prime is the same as this tau x prime y prime, right? But it's acting on this top face, as you see here. And then we can also put the appropriate tau xy and sigma x on this right side. This should be, yes, this should be vertical. It's a little bit unclear the way I drew it. It's a little sloppy, right? But this is vertical. And this is horizontal, all right? And so we can also do force balance to calculate out what sigma y prime is, right? So this is the repeat for y prime without needing to recalculate tau x prime y prime. So if we do our force balance and we calculate out tau x prime y prime here, we don't need to do it again when we create this diagram or this free body diagram, okay? So let's do an example. Let's say that we have a state of stress on an element that has sigma x equals 50 megapascals, sigma y equals 100 megapascals, and tau xy equals 0 megapascals, or 0, right? The question is, what are sigma x prime, sigma y prime, and tau x prime, y prime, when the angle of counterclockwise rotation theta is 30 degrees, okay? So in this case, this is going to be a positive z rotation. All right, z coming out of the board, and this is the state of stress, right? 50 megapascals, 100 megapascals, and there's no shear stress. So that makes our lives a little bit easier. We rotate, as you see here, by the specified amount theta, right, 30 degrees. And the element has rotated, and I can see, okay, this face is now rotated this way. This face is rotated a little bit that way, okay? And we can define the sigma x prime that we desire. We can define the sigma y prime that we desire in this problem. And we can also define our shear stress, tau x prime y prime, right, on this face, right, and then on these two faces as well, to keep this element, this new transformed element, in equilibrium. Okay, so essentially we haven't set up the triangle yet, but we've now defined the problem. Like I said previously, it's often very useful to exaggerate the angles that are involved. So 30 degrees is nice because, you know, it's going to lead to kind of this pair of 30 degrees and 90 degrees. That's kind of easy to keep track of. But sometimes even, you know, my angles are not going to be perfect here, but as I'm kind of drawing these triangles, I try to make them kind of big, kind of grossly exaggerated if I can, so that I see that, okay, the sine of 30 degrees is much smaller than the cosine of 30 degrees here. So that when we start, or when we, you know, define these surfaces, for example, right now, it's very clear that this is going to be the sine of 30 degrees. And it's clear that this is going to be the cosine of 30 degrees. And then when we start adding our other, or our original stresses, I guess I should say, we can also clearly mark the components. Okay, you see this now? This is now saying, look, I understand that sigma x is 50 megapascals, but like we said previously, this sigma x is not in the same direction as x prime, and is not in the same direction as, say, our tau x prime y prime. Okay, we haven't drawn it here yet. But I can divide this into its two components. 50 megapascals is the hypotenuse of a triangle, okay, that can be created, and we say we have vector addition. So this vector now is in the same direction as x prime, right? And this direction, this vector on this side, the sine of theta direction here, is going to be in the same direction as this face, which is where tau x prime y prime resides. Similarly, 100 megapascals is what we have for our sigma y, but sigma y is not in the same direction as x prime or y prime. Okay, so in order to take care of that, we break it into its components. And it's important to kind of keep track of, all right, it's going this direction, so head there, and then I add in this direction. Because when we do equilibrium, we need to be able to add these and subtract these vectors appropriately from each other. Okay, and here's tau x prime y prime. So what do? We perform equilibrium in the new reference frame. We're going to do equilibrium, force equilibrium. Fortunately, we don't have to do moment equilibrium. Okay, we just had to do force equilibrium. But it's going to be force equilibrium in the x prime direction and in the y prime direction. So here, as we are summing forces in the x prime direction, we often start with what we're interested in solving for. So sigma, in this case, x prime is going to allow us to solve for sigma x prime. When we do the y prime case, it's going to allow us to solve for the tau x prime y prime case, right? But we can see that tau x prime y prime, since it's orthogonal to x prime, it makes no contribution to sigma x prime. So sigma x prime is this one, in this direction, acting on this face, gives us this force. Now, it's sometimes easier to pick doing things on faces, okay? Or maybe it's sometimes easier depict things doing it on vectors. It doesn't matter. You can do it, but we just have to be careful and we have to account for all the contributors. So here we have our delta A cosine 30 degrees, okay? And that is a one face, which is going to be right here, so right here. And this vector is acting right in the x direction, but the component that's acting in the same direction as x prime is the adjacent. It's this vector right here. So this is where we get 50 megapascals, that's the hypotenuse, times cosine of 30 degrees to get this contribution. Okay, so this is if we get our heads around this relationship for this one, it's like rinse and repeat, okay, for the rest. Okay, but it's can be I think some people find this fun. I think get a little bit stressful when I had to do lots of trigonometry and not make a mistake. I get a little stressed, okay? All right, so that is one vector. All right, now we're going to jump down to this one, all right? And this vector, all right, the contribution that's in the same direction as x prime is this opposite side right here, okay? So that's going to be sine of 30 degrees, which is what you see here. And it's acting on the bottom face, which is delta A sine of 30 degrees, okay, like we see here. And then that's pretty much it. That is it in terms of what's contributing. There are two forces, and we have those directions that are associated with x prime. So we just set this equal to 0. And what do you do? Well, you solve for sigma x prime. You take out there are all these delta A's. You know, some people will probably just not write them either way, okay? But you take them out, you're going to cancel them out, and it's going to be sigma x prime is equal to 50 megapascals cosine times cosine of 30 degrees times cosine of 30 degrees plus 100 megapascals times sine of 30 degrees times sine of 30 degrees, right? These minuses become positives. And so this is what you get. This is what we get. All right, so, and it's good to make a little check here, all right? You can kind of see here that we've rotated, right? Sigma x prime is going more towards the sigma y, all right? And it's 50 megapascals here. And if it were to go 90 degrees, it would then become 100 megapascals. So this is good. This is a good check. It's like, okay, we went 30 degrees. We had an increase. We didn't go to 45 degrees. Like these transformations become more clear, but it increased because it got more aligned with the sigma y direction, which is greater than the sigma x, okay? Or sigma y is greater than sigma x. Okay, so this is taking a long time. Thank you for your patience. Now we're going to do the summation of the forces in the y prime direction, all right? And we have tau x prime, y prime acting on the delta A face, all right? That's this one acting over here. And then we're going to add to it what? This is maybe a little counterintuitive. You're like, well, this was going minus direction. Yes, but look, this opposite side is actually in the same direction as this green vector over here for the tau x prime, y prime. So we add, okay, on this face, or on this, for this vector in this direction, and it's acting on the delta A cosine 30 degrees face, and so that's what we get. We come over here and we're like, okay, this vector is going down, and I need something that is parallel to this green vector, the tau x prime, y prime. It's got to be this component. It's definitely going the opposite direction. It's pretty clear. So we can use the cosine, okay, of theta here times 100 megapascals times the delta A sine 30 degrees. Okay, and those are the two components again. Set this equal to 0, and voila, we get 21.65 megapascals. All right, and you know, this might make a little sense too, because we had 0 originally. Okay, tau xy was equal to 0, but now we've rotated, and we see that we have, you know, two normal stresses here and it's now no longer non-zero, okay? And it might give us a little bit of intuition that it's even become positive. Okay, so let's keep going. And what are we going to keep going about? We're going to think about sigma y prime because we haven't solved for that. Okay, so what do? Well, same thing we did before, except we need to take a cut in a different orientation. So this one's nicer than the one I showed previously, right? This side of the triangle is a little more vertical to line up with this face of the stress element that we start with. And I'll go through this a little more quickly here, but we have our delta A being here on this face. This is the delta A cosine 30-degree face. This is going to be the delta A sine 30-degree face. We can take our stress that's horizontal and break it into its two components. So this is sigma x now being broken down into components that will be parallel to this tau x y prime, tau x prime y prime, and also the sigma y prime, or the y prime direction. Okay. Similarly, we break down the 100 megapascals that we have, okay, into its components acting on this face, and we can write sigma y prime, and we can write tau x prime y prime, right? These are, this is the tau x prime y prime that you see here, and this is now the sigma y prime coming out, right? So this is like the top face of this rotated element, okay? We do equilibrium, again, and I'll go through this kind of quickly, but we go through and we figure it out in the y prime direction, and we're going to multiply by delta A, the sigma of y prime, we're going to multiply by delta A to get a force. We use the appropriate component from our sigma x on its appropriate face. And again, similarly, appropriate component from the 100 megapascals, the sigma y, acting on this bottom face. And we set it equal to 0. And if you like, you can plug this into Python, right? So the Colab has this up for you if you like to kind of do or check some things and make sure these calculations are right. And we get that sigma y prime is now 87.5 megapascals. So again, that kind of makes sense. It was at 100 megapascals, but I've rotated a little bit. And I remember I gained some in the tau and in the tau x prime y prime and the sigma x prime. So it makes sense that I lose a little bit in the sigma y prime. Okay. Let's do another example. All right. This one is more complicated because tau xy is not 0. Okay, so that means that we're going to have more forces, more stresses, and thus more forces acting on these cuts, and we're going to need to do a little bit more careful job of counting. Now, another thing that you might see in mechanics problems is that often there's a surface being defined not in terms of a rotation, but in terms of an angle of a slice. So, you know, maybe there's a bar that's being extended, but now, or under tension, and now we want to know what's the depicted state of stress at a rotated angle, not just like normal to the bar, but at a rotated angle. So this can be a little bit subtle and a little bit tricky to think about. Again, if we use exaggerated triangles, this becomes easier to understand. So we're asking, I wrote with sigma x prime normal and to the right of the shown slice. Okay, so that's this face, and then sigma x prime needs to come out of that face. Well, if I look at it, I can take this side, and it means I'm kind of like rotating it actually a little bit negative, just a little bit like that. So we get that this is the 30 degrees, all right, or it's actually kind of like a minus 30-degree rotation, the way we normally define things, okay? Because if you saw here, right, this is how theta is often defined, okay? And now we're going the opposite direction, okay? So again, a little bit trickier. We want to be careful and keep track of our counting. So that vector coming out is going to be the sigma x prime, okay? And we have our sigma y prime going up out of the top surface, right? Of this, and it's like, oh, I could tilt it a lot more, but I'm trying to keep it slightly exaggerated. And in this case, slightly exaggerated means don't tilt too much, okay? And then we can put our tau x prime y prime on this. And I want to go a little bit quickly here. This is an interesting cut, right? What are we doing? So these are the edges of the old element, and this is a cut now that we've made, and we're defining this as 30 degrees in here. All right. So again, want to be very careful, but remember the hypotenuse is associated with the new x prime direction here. And what's also nice, if you look at this problem, I should have mentioned this previously, but they're not asking us for sigma y prime, just for sigma x prime and tau x prime y prime. Or I could have put down, let's do sigma y prime and tau x prime y prime. This means that we only had to make one triangle, okay? Because we can figure out, just one of the normal components and the shear stress, and the shear stress can come from either of the triangles. Okay, so again, we define the faces of the opposite and adjacent portions of the triangle. We make sure we keep track of the hypotenuse associated with sigma x in this case, also the hypotenuse associated with sigma y and its components, break it down, right? And now we also have these components associated with shear stress. Now, this shear stress here is this shear stress here, okay? See that? This shear stress here is this shear stress here. So these are the original tau xy, okay? That's the 75 megapascals. And the shear stress we're interested in figuring out is going to be this new one on this slanted face, tau x prime y prime, all right? Once the triangle is drawn, that's kind of the hard part, or I think it's part of the hard part, then it becomes a matter of keeping track of things and doing the algebra appropriately, okay? And so we'll kind of, you can take a look at these if you like, slow it down, whatever you want to do, but you can see that when we're solving for x prime or the sigma x prime direction, right, we have two options for these vectors, right? And now there are 4 contributing vectors, right? Sigma x, sigma y, and then 2 tau x prime y primes on this, all right? So this is the sigma x prime or sigma x contribution, so that's like we had before. But this one right here is a contribution from this vector, all right, the 75 megapascals. And what we're saying, okay, is that if we want this little piece right here, that's in the same direction as sigma x prime. Okay, so this is going to be the sine of 30 degrees acting on the delta A cosine 30 degree face. We have our contribution from sigma y prime, and we know how to do that because we did that in the previous example. And then again, we have a contribution from a shear stress, and we're acting in this direction, so we're going to want this side of that triangle, okay, right there, and that's going to be cosine of 30 degrees, and it's acting on the delta A sine 30 degree face, and so now it's equal to 0. So when we do these and have a shear stress, we have before we had 3 components if you count the sigma x prime delta A, all right, when there was just no shear stress. But once there's shear stress, we can expect 5 components, all right, that we have to keep track of. And this is the associated Python that I put in so that I didn't have to, punch it into my calculator, but sure, you can punch it into a calculator if you like. And the resulting sigma x prime is, as you see here, minus 2.45 megapascals. So this is kind of interesting too, okay, because even though we defined it, right, to be positive, it actually ends up going in. So we actually are in a slight state of compression in this orientation, compression in the x prime direction. Okay. nothing's changed here, so I'm just writing that down again. And now you can do this. We can do the summation in the y prime direction, equilibrium. Okay, and it's the same idea. I'm actually going to go through this just pretty quickly, but feel free to check these, stop the video, look, make sure that it's clear where each of these components is coming from. And as we said previously, there are 5. Okay, the tau x prime y prime delta a, right? And then there are 4 vectors of stresses that came from the original element, or the original orientation of the element. And you can plug that in and get a calculated result. All right. So that is the content I wanted to share for the first portion. The next 2 portions, I promise, will be much shorter. Okay. Here's a question. There are 2 questions to ask here. All right. One for you all is to say, okay, I have an element on a cylindrical pressure vessel, and normally, right, I define a longitudinal and a hoop stress, a hoop direction, okay, as we see here. And the question is, if I rotate this element 45 degrees, what is the magnitude now of the shear stress on this element? Okay, if we start with this state of stress and we've rotated it 45 degrees. Okay, so that's a problem for you all to work on. And the second one is more similar to what we were doing before, in that take an element with prescribed state of stress, and then we're going to do a slice. Okay, in this case, right, we're going to say that slice with this component is 70 degrees. All right. What is this really? This is really like the sigma x prime coming out with a rotation of 30 degrees. Okay, so however you want to do it, you can make the triangles, right? But you're gonna want to make sure that you're keeping track of the angle appropriately, and I suggest exaggerating the triangles. All right, thank you very much for getting through this. This was a little bit longer than I was hoping, but these principles are important, and they can be very confusing. Okay, so there are a couple here that can give us a chance to practice and make sure that we we keep track of things appropriately in our accounting. Okay, see you soon.